Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind, and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into one of the strangest and simplest puzzles in the universe. We'll trace the shadowy outlines of black holes, those quiet, invisible anchors of gravity that hide their secrets behind silence. But more curiously, we'll ask how something so mysterious can be described by just 3 numbers. Before you settle in and get cozy, I'd love it if you could take a moment to like this video and subscribe, only if you truly enjoy these gentle wanderings. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. I always love seeing the constellation of quiet minds that gather here. Now, dim the lights, maybe turn on a fan or let the window breathe a little. Tonight, we'll drift into a cosmic riddle about black holes, information, and why simplicity might not be simple at all. And if your thoughts start to wander, let them. We'll still be here, unfolding the story, one gentle turn at a time. Let's begin with something familiar. The moon. You know its shape. You've seen it hang above rooftops, peek through trees, glow behind clouds. To describe the moon scientifically, though, to really capture what it is, you'd need a staggering amount of information. You'd need maps of its craters and mountains, data on its orbital patterns, models of its dusty regolith, chemical breakdowns of its surface, even historical data on how it formed and how it's changed. The moon, for all its quiet familiarity, is a deeply complex object. You could write libraries about it and still miss something. Now imagine something that defies that expectation. Picture a black hole, not in a dramatic, swirling sci-fi way, but as it truly is. An object with no surface, no texture, no ridges or valleys or colour. Just an event horizon. A boundary that's not a wall, but more like a limit. A horizon where space folds inward and anything that crosses it disappears from view forever. Now here's the strange part. To describe a black hole, a real, physical, scientifically accurate black hole, you only need 3 numbers. That's it. Just 3. Mass, electric charge, angular momentum, its spin. That's all. It doesn't matter what the black hole used to be. A star, a cloud of gas, or even a pile of spaceships and encyclopedias and leftover lasagna. Once something falls in, everything about it is stripped away. What's left is a region of space defined solely by mass, charge, and spin. These 3 parameters are all that can be known from the outside. There are no identifying features, no texture, no labels, just those 3 numbers. This idea is known as the no-hair theorem. It sounds a bit silly at first, no hair, but in physics, hair refers to additional distinguishable features, like the chemical makeup of a star, or the bumps on a planet, or the colour of an object. Hair is complexity. It's information. A black hole, by this theorem, has no hair. It offers no hint of what fell into it. So here's the puzzle. How can something that swallows complexity so completely be understood so simply? It's like walking into a room full of people, some laughing, some reading, some staring out the window, and someone shuts the door. From outside, all you can know is that the room weighs 200 kilograms, has a bit of static charge, and is slowly spinning. What happened to all those people? What were they doing? What stories were inside? The door never opens again, and all you get are 3 numbers scribbled on a sticky note. It feels wrong, doesn't it? But this is not just imagination. These 3 numbers are not merely approximations. They're mathematically exact descriptions of black holes under general relativity. The solutions to Einstein's field equations, the very structure of spacetime itself, lead to this result. For a given set of conditions, a black hole will settle into a state described only by those values. Nothing more. This unsettling elegance has been studied for decades. It's been tested, refined, and accepted by physicists all over the world. But just because a rule holds doesn't mean it's comfortable. In fact, the simplicity of black holes might be the most uncomfortable thing about them. Because if a black hole really does erase everything except 3 traits, if everything else about the matter that formed it is permanently lost, then we've run into something that physics is not quite prepared to handle. You see, physics doesn't just describe how things look or behave, it also holds on to a deeper commitment, one that's not often spoken aloud, but which underlies all our theories. The commitment to information, that what is matters, that every arrangement of particles, every interaction, every subtle flicker of energy leaves some kind of imprint. But in the world of black holes, that imprint disappears, at least from the outside, and so begins the paradox. It starts softly, a contradiction between what gravity predicts and what quantum mechanics demands. And it grows as scientists try to reconcile the two. And soon, we're not just talking about black holes anymore. We're talking about whether the universe itself is understandable, whether reality has memory, whether information can truly be lost. For tonight, though, we'll let that contradiction unfold slowly, gently, like a ripple in a still pond. We'll let each piece reveal itself, not as a sharp equation or a complicated lecture, but as a quiet question whispered by the universe. How can something be so simple and still hold so many secrets? That's where we'll go next. Imagine something falling, not dramatically, not all at once, but gently, gradually, like a leaf giving in to gravity. Picture a star, enormous and burning bright, living out its final days. Its fuel runs out, pressure collapses inward, and then, in one swift and silent moment, the core implodes, the surface vanishes, the light goes out. What's left behind isn't just darkness, it's geometry, twisted in a way that nothing can escape. At the heart of a black hole is not a place exactly, but a boundary, a threshold. It's called the event horizon. And while the name might sound like something out of a science fiction novel, it's a very real mathematical feature of space-time. It's not made of matter or light. It's not solid, or even thin like a membrane. It's simply the place where escape becomes impossible. Anything that crosses it, particles, waves, even the rules of causality, can no longer return. And the strangest thing about this boundary is how featureless it is. Unlike a mountain or a moon crater or a swirling galaxy, the event horizon has no bumps, no waves, no fingerprints of the things that fell in. It doesn't ripple with memories of a collapsing star, or shimmer with the shape of what was lost. You could throw in a sculpture, a library, a forest, a thunderstorm, and the event horizon would look exactly the same as if you had thrown in a single pebble of equal mass. That's because in the language of general relativity, the black hole doesn't care how something fell in. Only that it did, and only how much mass, how much spin, and how much charge it added. From the outside, a black hole is a curve in space, a kind of hollow, where geometry bends inward so steeply that all paths point one way, in. It's shaped by gravity, but it's not a thing in the traditional sense. There's no surface you can stand on, no crust or core. Just a region where all known paths lead deeper, and no map shows a way back out. To visualize this, many physicists use the metaphor of a rubber sheet. Imagine a flat, stretchable sheet, like the surface of a trampoline. Place a bowling ball in the centre, and it creates a dent. Now imagine rolling marbles nearby. They spiral inward, caught by the curve. That's the gravitational pull. If the dent is deep enough, infinitely deep in fact, then not even light can escape. That's your black hole. But the sheet doesn't tell you what the ball is made of. It only shows how the surface curves, and so, black holes become objects without identity. This is not just a poetic notion, it's built into the math. The Kerr solution, which describes rotating black holes, gives a perfect description of the exterior space-time around them. And no matter what kind of matter originally collapsed, whether it was hydrogen, helium, or even antimatter, the resulting geometry is the same, as long as the mass and spin match. In physics, this is sometimes called uniqueness, but it feels more like forgetfulness. The black hole has no memory, not of the shape of the collapsing star, not of the direction of its magnetic fields, not of the planets that orbited it, or the poems broadcast from nearby satellites. All of that vanishes beyond the horizon. It's not that it's hidden, it's that it's erased from the perspective of anyone outside. Now it's worth pausing to note, this behaviour is radically different from anything else in the universe. If you crush a building into rubble, the rubble still contains clues, bits of brick, fragments of wiring, layers of dust that a geologist or forensic scientist might examine. Even in destruction, there are traces. But a black hole doesn't just destroy the structure, it severs the thread of history. From the outside, we can't tell what happened. There is no reconstruction, no footprint. This is where the story starts to feel less like science and more like a riddle. How can something be so completely defined and yet completely unknowable? Physicists used to accept this strange forgetfulness as part of the deal. Black holes were rare, extreme, distant. Their oddities were seen as curiosities, not crises. But as our understanding deepened, and as black holes moved from theoretical to observable, the problem became harder to ignore. Because if a black hole really does erase all the details of what fell in, then it violates something very important, not a law of gravity, but a principle far more delicate, the conservation of information. And that's the heart of the puzzle. In classical general relativity, the event horizon marks a one-way surface. Everything goes in, nothing comes out. But in quantum physics, the set of rules that govern particles, atoms, and all fundamental interactions, this doesn't sit well. In quantum theory, information can't be destroyed. Not even in the collapse of a star. Every particle interaction, every wave function, contains data that, in principle, should remain somewhere, somehow, in the universe. And so, we are left with a tension. On one side, Einstein's elegant spacetime, curving around mass and collapsing into black holes. On the other, the fragile, intricate tapestry of quantum theory, which insists that the universe keeps records. Somewhere between those two truths is a paradox, one we haven't fully resolved, but we'll get there, slowly. For now, just rest with the image. A perfectly smooth surface in space, not marked by time or texture, just gently enclosing a region of no return. It doesn't glow. It doesn't pulse. But it holds a question as deep as the universe itself. If a black hole doesn't remember what went in, then where did the memory go? And if the universe forgets, what else might it let slip away? At first, it was just a curiosity, a kind of mathematical magic trick tucked into the heart of Einstein's theory. You could imagine physicists in the early 20th century sketching out possibilities on blackboards, rotating solutions, charged ones, idealized stars that collapse inward not into explosions but into silence. They weren't sure if these objects existed. They certainly didn't expect to find them sprinkled across the cosmos. But even then, something about black holes didn't sit quite right. The deeper they looked into these strange geometries, the more it seemed they weren't just oddities at the edge of physics. They were paradoxes wrapped in equations. Not because the math was wrong, but because it might be too clean, too perfect, too willing to hide its steps. That's where the question began. It wasn't loud, it wasn't even new, but it echoed. And over the years it got sharper, deeper, more uncomfortable. It asked something simple, and yet the universe, so far, hasn't been able to give a simple answer. The question is, where does the information go? To someone not steeped in theoretical physics, this might not seem like a big deal. Things fall into black holes. They're gone. End of story. But in science, especially in quantum mechanics, information isn't just a label or a name tag. It's a principle, a promise, that the past is never truly lost, that even the most delicate arrangement of particles, the faintest shimmer of energy, is not erased but transformed, that if you had perfect knowledge of a system, you could in theory run the clock backward, rewind the universe, recover what was. This isn't science fiction. It's baked into the rules that govern our world. From the quantum scale to the thermodynamic scale, information is supposed to be preserved. It might be scrambled, buried, or wildly complex, but it doesn't vanish. Entropy increases, yes, but the underlying information, how things came to be as they are, stays embedded somewhere in the system. That's why black holes are so unsettling, because if something falls into a black hole and that black hole later evaporates, slowly radiating away its mass through Hawking radiation, what remains? The mass is gone. The hole has vanished. But what about the patterns, the relationships, the information about what fell in? Let's pause for a moment to picture that. Imagine throwing a diary into a fire. The paper burns, the ink curls away, the cover blackens and cracks. But in theory, if you had a perfect model of every molecule in the fire and the air around it and all the energies involved, you could, at least hypothetically, reconstruct what the diary said. You could reverse the combustion. You could read the words. But if you throw that same diary into a black hole, and the black hole evaporates over billions of years, there is no known mechanism, no hidden trail, no whispered echo left behind. It's not just unreadable, it's as if the story was never written. That violates unitarity. And unitarity in quantum theory is sacred. It's the idea that the evolution of a system is reversible, that information flows forward but isn't erased. If you break unitarity, you don't just break a rule, you shake the foundation of the entire theory. You suggest that the universe, under certain conditions, can shrug off its history, that there is a leak in the book of reality. This, then, is not a small question. It is one of the deepest puzzles in modern physics, and it gets stranger. Because Hawking radiation, the glow that allows black holes to slowly evaporate, is, by all our calculations, completely random. It doesn't appear to carry any specific information about what fell in. It's thermal, featureless, a kind of quantum static. And if that's true, if black holes evaporate into meaningless noise, then information really is destroyed. That's the contradiction. Because it shouldn't be. Quantum theory forbids it. General relativity allows it. And somewhere, deep in the fabric of these two great theories, is a fault line that won't close. It's not a matter of experimental error or misunderstood data. It's a collision between frameworks. The universe, it seems, is playing by two sets of rules, and when those rules meet at the edge of a black hole, they disagree. This is where things shift from strange to profound. Because suddenly, we're not just talking about a region of curved space. We're talking about the boundaries of what physics can explain. We're talking about the very idea of truth in a scientific theory. If information can vanish, what else might slip through the cracks? What is the meaning of causality, if not every cause leaves a trace? What is the meaning of measurement, if outcomes can be erased? What is memory, not just in brains, but in the universe itself? In this way, black holes don't just challenge our understanding of gravity. They force us to confront the limits of knowledge. They ask whether the universe is a story that remembers itself, or one that occasionally forgets. And still, the question whispers, where does the information go? Some scientists think it stays, hidden in the Hawking radiation in ways we don't yet understand. Others believe it's stored on the event horizon itself, like a cosmic hologram. A few suggest that maybe we're asking the wrong question, that where and what and how lose meaning at the edge of a black hole. But we're getting ahead of ourselves. The path to answers will take time. It will wind through thermodynamics, quantum field theory, string theory, paradoxes and poetic possibilities. but for now, it is enough to sit with the discomfort, to marvel at the way the universe can be both knowable and unknowable in the same breath, to let the question settle beside you as you drift closer to sleep. A black hole is a shape with no memory, but you're made of memories, of patterns, echoes, soft arrangements of particles held together by time and thought. Maybe that's why this paradox stings a little, because if the universe can forget something so completely, we wonder, could it forget us too? For now, rest. The journey continues. It might surprise you to know that the idea of a black hole, an object so dense that light itself cannot escape, didn't begin with Einstein. It began quietly in the 18th century, long before the modern understanding of gravity or the nature of light. It began with a man named John Michell, an English natural philosopher whose work was mostly forgotten in his own time but now seems astonishingly prescient. In 1783, Michell considered what might happen if a star were massive enough and dense enough that its escape velocity, the speed required to break free of its gravitational pull, exceeded the speed of light. Using Newtonian physics, he worked out the conditions under which such a star could exist. He called it a dark star, not because it was mystical, but because its light quite simply couldn't get out. It was a thought experiment, not a prediction. At the time, light was thought of as tiny particles, corpuscles, and gravity was a force that reached across empty space, pulling objects toward one another. It wasn't a bad guess, given the tools he had, and yet Michell had no idea how close he was to something real. The idea faded into obscurity for over a century. Newtonian gravity, while remarkably successful, could not fully explain how gravity affected light, or what happened when objects became truly extreme. It took the mind of Albert Einstein to shift the conversation from force to geometry. In 1915, Einstein published his theory of general relativity, a new vision of gravity that wasn't about invisible strings pulling on masses, but about how mass and energy curve the very fabric of space-time. In this framework, what we call gravity is simply the way objects move through a curved landscape. A planet orbits a star not because it's being pulled, but because it's following the straightest possible path in a space that's been bent by the star's presence. Light too follows these paths. It travels along what physicists call null geodesics, lines that are straight in curved space. But if the space is curved enough, those lines can loop inward, trapped in spirals from which escape is impossible. And if the curvature becomes extreme enough, the very structure of space folds back on itself. The straightest line leads deeper in, and there is no path outward. This is where the concept of a black hole emerges, not from fantasy, but from the very logic of Einstein's equations. Just a few months after Einstein introduced general relativity, a German physicist named Karl Schwarzschild, while serving on the front lines of World War I, found the first exact solution to those equations. It described the gravitational field outside a perfectly spherical, non-rotating mass. This solution revealed something startling. If enough mass were compressed into a small enough region, space-time would become so warped that not even light could escape. The distance from the centre of such an object to the point where escape becomes impossible is known as the Schwarzschild radius. Cross this invisible line, and you're no longer just falling, you're falling toward a future from which return is not possible. That line is the event horizon. But all of this, the curved geometry, the event horizon, the trapped light, was still purely theoretical. No one had ever seen a black hole. No one even knew if they could form. After all, the Schwarzschild solution assumes a perfect sphere, in a vacuum, unaffected by the messy chaos of real stars. It was elegant, yes, but was it real? Physicists debated. Some believed that nature would find a way to avoid forming such an object. Others suspected that if conditions were right, if a massive star exhausted its nuclear fuel and collapsed inward, there might be no force strong enough to stop it. In that case, a singularity would form at the centre, hidden behind an event horizon, and a black hole would be born. But they had no evidence, just equations and arguments and the quiet gravity of an idea. And yet, the math persisted. It kept showing up in different forms, in rotating systems, in charged objects, in collapsing stars. Each time the conclusion was the same. Once mass crosses a certain threshold and compacts tightly enough, the curvature becomes inescapable. Light bends in, not out. And the region that forms has no surface, no inside you can visit, just a horizon, a threshold, and the promise that whatever lies beyond it is cut off from the rest of the universe. It's strange to think that the concept of a black hole, so dark, so extreme, so modern, was born not in a laboratory, but in letters and calculations, in trenches and notebooks, long before anyone had seen one. Back then, they were ghosts in the equations, possibilities. But as we'll see next, they didn't remain ghosts for long, because eventually we began to find them, not with our eyes, but with instruments tuned to invisible light. We didn't see them directly, but we saw their shadows. We saw the way they bent space, stirred stars, devoured matter, and we realised they were out there, not just in theory but in truth. But before we get there, take a moment to breathe, to feel the weight of this quiet realisation. Gravity doesn't just pull, it folds, it curves, it builds traps with no walls, doors with no return. And somewhere in that silent collapse of possibility is the beginning of a mystery we're still trying to solve. It was the winter of 1915. Europe was at war. Soldiers trudged through trenches, machines churned mud into chaos, and above it all, far from the noise of artillery, the sky remained silent. In this strange moment, when the world was coming undone, a physicist named Karl Schwarzschild, serving on the Eastern Front, found himself captivated by a different kind of collapse, one not of nations or empires, but of stars. He had read Einstein's newly published theory of general relativity, a set of equations so revolutionary they reshaped the very idea of space and time. And instead of pushing it aside, Schwarzschild did something astonishing. He solved them. His solution wasn't messy or approximate, it was exact. He found the precise way space-time would curve around a single spherical mass in a vacuum. And within that solution was something strange, something the equations seemed to allow, but that no one expected. A boundary. A place where the math broke down, not because it was wrong, but because it was pointing towards something we didn't yet understand. That boundary would later be called the event horizon. Let's take a moment to understand what that means. Imagine a perfectly spherical star floating alone in space. Now imagine squeezing it, more and more tightly, until it reaches a critical radius, the Schwarzschild radius. At that point, its gravitational pull becomes so strong that nothing, not even light, can escape. The star has become a black hole. But not in the way most people imagine, not as a swirling drain or a cosmic vacuum cleaner, but as a region of space from which information cannot return. Outside this radius, gravity still acts normally. Light can travel, space behaves predictably, time flows forward. But cross that invisible line, and everything changes. Inside the Schwarzschild radius, all directions point inward. There is no out. No matter what you do, how fast you move, or what technology you use, escape is no longer possible. It's not a wall, it's not a surface, it's a one-way door built into the geometry of space-time itself, and at the very centre, if the collapse continues unchecked, there lies a singularity. Now, the word singularity sounds dramatic, but in physics, it simply means that the math gives us infinities. In this case, the equations predict that density becomes infinite, space-time curvature becomes infinite, and the laws of physics as we know them break down. It's not a place, not in any meaningful sense. It's a point where our understanding ends, a kind of cosmic full stop, a place where questions go in and no answers come out. But back to Schwarzschild. His solution was elegant and complete, but even he didn't claim that such objects actually existed. It was a mathematical curiosity, a black hole in the equations, but not necessarily in the universe. For decades, physicists debated what Schwarzschild's solution really meant. Some argued that the singularity was a flaw in the math, something that a better theory would eventually remove. Others suspected it was real but hidden. Nature, they hoped, would find a way to avoid such an extreme fate, perhaps through pressure, rotation, or some quantum mechanism we didn't yet understand. In a sense, they were right to be cautious, because black holes, if they existed, would be objects unlike anything else in the cosmos. They would not radiate light, they would not reflect it, they would give off no surface heat, no sound, no chemical signatures. You couldn't poke them or prod them, you couldn't bounce a signal off them, you couldn't land on them. They were pure geometry, curvature, mass, spin, without texture or trace. In a world where science advanced by measurement, black holes seemed, for a long time, beyond the reach of experiment. But there was something unsettling about their inevitability. Because as our understanding of stars improved, and as we began to model what happened at the end of a star's life, it became clear. If a star was massive enough, and if it exhausted its nuclear fuel, there really might be no force in the universe strong enough to stop it from collapsing. In stars like our Sun, the story ends gently. The outer layers drift away, and the core cools into a white dwarf, a dense but stable ember. Slightly heavier stars collapse further, forming neutron stars, where matter is crushed into a soup of neutrons so dense that a teaspoonful would weigh billions of tons. But if the star is truly massive, several times the mass of our Sun, then not even neutron pressure can hold it up. The collapse continues, relentless, final. And that's when the Schwarzschild radius becomes real. That's when the event horizon forms. That's when a black hole is born, not just in equations, but in the fabric of the actual universe. And still, the outside doesn't know what happened inside. You could watch the collapse from afar, and as the surface of the star approached the event horizon, time would appear to slow. Light would redshift. The image would stretch and fade. Eventually the star would vanish, not in a flash, but in a kind of cosmic silence. A disappearance, not an explosion. And so the first mathematical black hole, once curiosity scribbled in the margins of wartime notebooks, became something more, a prediction, a warning, a window into a place where space and time had no exit. We still didn't know if these objects were out there. We hadn't found one yet. But the math was clear, the logic was sound, and the sky. Well, the sky was about to offer its own evidence. But before we look up, let's pause again. A black hole, born from a collapsing star, is not a monster or a mouth. It's not a thing at all. It's a region of space defined by a boundary, shaped by a story that ended in silence. It is the geometry of surrender, the final curve of gravity, drawn not in ink or chalk, but in the very fabric of reality. And all it takes is enough mass, enough collapse, enough time. The universe, it turns out, doesn't need drama to build mysteries. Sometimes it just lets things fall. For a long time, black holes were like ghosts in the equations, mathematical whispers without proof, elegant curves drawn by gravity that no telescope could see. Physicists believed in them the way you might believe in a faraway mountain veiled in mist. You trust it's there because the map says so, because the terrain hints at it, because the story leads in that direction. But still, a part of you waits for the moment when someone actually sets foot on the slope, or catches its outline in a photo. And then, one day, someone did. It wasn't a photograph in the usual sense. No glimmering black dots surrounded by fire. In fact, the first real clues didn't come from seeing black holes directly at all. They came from what black holes do to their surroundings. Like a person moving silently through a room, knocking over chairs and ruffling curtains, a black hole announces itself not by what it is, but by what it disturbs. In the 1960s and early 70s, astronomers were peering at the sky in new ways. They had begun listening to the cosmos in X-rays, a kind of light invisible to human eyes but powerful and penetrating. And in those higher frequencies they began to notice strange, flickering sources, intense bursts of energy coming from compact regions of space. One of the most famous of these was Cygnus X1, located in the constellation Cygnus the Swan. It didn't look like much through a traditional telescope, just another dot in a starry sea, but in X-ray readings it flared and danced. Something was feeding there, something unseen. It turned out that Cygnus X1 was part of a binary system, a pair of stars orbiting one another. One of them was visible, a bright blue giant. The other was missing, invisible, and yet its gravitational presence was unmistakable. The visible star wobbled, tugged by an invisible partner. Matter from the star was being pulled into the void, forming a swirling disk of superheated gas. As the gas spiraled inward, it accelerated, compressing and heating until it glowed fiercely in X-rays, radiation we could detect from Earth. This was no ordinary star. It was too small to see, too heavy to be ignored, too hungry and too quiet. All the data pointed in one direction. This was a black hole. It wasn't the only one. As X-ray astronomy improved, more systems like Cygnus X1 were found. Binary stars where one member had vanished from sight but left behind a gravitational fingerprint. These were the first stellar mass black holes, remnants of once massive stars that had collapsed past their limits, through neutron states, beyond pressure, into shadow. They weren't everywhere, but they weren't rare either. It seemed the universe had been making them quietly all along, and we were only just learning how to listen. But even that was just the beginning, because soon astronomers began to suspect that some black holes were far, far larger than anything a single star could produce. At the centres of galaxies, including our own Milky Way, there were signs of something massive, something still, something invisible. Stars in the galactic core moved too fast, circled too tightly, as if pulled by a gravitational anchor with no light. Observations of the centre of the Milky Way over many years showed stars orbiting a common centre with incredible speed, completing full loops in just a few decades, despite the distances involved, and what they orbited wasn't visible at all. This unseen mass, packed into a region no larger than our solar system, had the mass of over 4 million suns. There was no other explanation, no cluster of stars, no dense cloud, no hidden trick. It had to be a supermassive black hole, and once we knew how to look, we found more of them, at the hearts of other galaxies, even in galaxies so far away that their light had travelled billions of years to reach us. Some of them were still feeding, swallowing gas and dust and even stars. These feeding giants, called quasars, shone brighter than entire galaxies, not because the black holes themselves emitted light, but because the matter falling in was stretched, torn, and heated to unbearable brilliance on the way down. It became clear, black holes are not rare cosmic accidents. They are part of the architecture of the universe. They are born in the deaths of stars. They grow in the centres of galaxies. They shape the orbits of stars, stir the evolution of galaxies, warp the path of light itself. And they do all this silently. This silence, paradoxically, is part of their power. Because while we can't see them directly, their effects ripple through everything around them. They are the unseen composers of cosmic structure, the invisible anchors of stellar cities, and perhaps most humbling of all is the realization that we live in a galaxy shaped by one of them. At the heart of the Milky Way, beyond the swirl of arms and the dance of planets and the orbit of the Sun, there lies a dark and massive presence. It has no name, no face, no surface to touch, but it's there, like a breath held for billions of years, watching, waiting, holding the galaxy in its curve. We call it Sagittarius A, and it is ours. It's strange, isn't it? To think that something so quiet, so invisible, so mathematically simple can have such enormous influence. But perhaps that is the nature of black holes. They remind us that not all power is loud, not all change is visible, and not all mysteries come with warning signs. Some of them just sit in the dark and shape the world around them. There's a quiet kind of mystery in heat. We tend to think of it as something simple. Temperature, warmth, the comforting hum of a radiator on a cold evening. But in physics, heat is a signal, a whisper of hidden information. Every warm object is alive with motion, with jittering particles, with collisions and vibrations too small to see. And behind that warmth is something deeper, entropy. Entropy is one of those words that sounds more complicated than it needs to be. In everyday terms, you might think of it as disorder, the way a tidy room becomes messy, or a cup of coffee cools as heat flows out into the world. But at its heart, entropy is really about possibility. It's the number of ways something can be arranged on the inside, behind the scenes, without changing how it looks on the outside. A melting ice cube and a lukewarm puddle might weigh the same, might even look similar from a distance. But the puddle has more entropy because the molecules are freer, more jumbled, more random. There are more ways to rearrange them that still look, on average, like a puddle. And in physics, entropy isn't just a description. It's a law. The second law of thermodynamics says that entropy in a closed system tends to increase. It's not just that messes happen, it's that, over time, the universe tends towards states with more possibilities, more disorder, more hidden microstates. So what happens when something falls into a black hole? At first glance, you might think entropy just disappears. A chaotic object, full of particles, complexity, history, falls past the event horizon, and all that remains is a smooth, silent shadow defined by three numbers: spin, charge, mass. It feels like a cheat. This troubled a young physicist named Jacob Bekenstein. In the early 1970s, he proposed something radical. He suggested that black holes must have entropy, that their simplicity on the outside was misleading, that in some fundamental way the information that had fallen in wasn't gone. It was encoded on the surface, not in the interior, not hidden in the singularity, but written, somehow, on the event horizon itself. Even stranger, Bekenstein calculated that the entropy of a black hole wasn't proportional to its volume, as you might expect from a normal object, but to its surface area. That's right. Not the space inside, but the boundary. It was as if everything that had ever fallen in, every atom, every arrangement of matter, was flattened and recorded on the edge. The bigger the surface area, the more entropy, the more room for information. To some, this seemed absurd. It broke intuition. Why should a three-dimensional object carry its information on a two-dimensional surface? How could something with no inside, no texture, no structure, encode complexity at all? And yet, the math worked. Bekenstein's proposal made sense of the disappearing entropy problem. If black holes had entropy, real, calculable entropy, then the second law of thermodynamics could still hold. The universe wouldn't be losing information. It would just be hiding it in a place we couldn't see. It was a beautiful idea, a bold one. And for a while, not many believed it. Because there was a catch. In order to have entropy, a system must have temperature. And in physics, temperature means radiation. A warm object glows. It emits energy. That's why stars shine. That's why your skin radiates infrared light. That's why the cosmic microwave background hums with the afterglow of the Big Bang. But black holes, by definition, absorb everything. Not just matter, but light. They don't shine. They don't glow. They don't radiate. If they had temperature, that temperature couldn't escape. And if it couldn't escape, how could it be measured? How could it be real? That's where the idea stalled. Bekenstein's entropy was elegant. It solved a paradox. But it clashed with the image of a black hole as a perfect absorber, a cosmic one-way street with no outward voice. And yet, something was stirring in the equations. Because at the edge of a black hole, something peculiar happens. A boundary forms, not just in space, but in understanding. Quantum mechanics, the theory that governs the very small, starts to whisper at the edges of general relativity. And those whispers were about to get louder, not from Bekenstein, but from another physicist. One whose mind was tuned to both the harmony of mathematics and the subtle dissonance of contradiction. His name was Stephen Hawking, and he was about to change everything. But before we follow him, let's linger here, just a little longer. Imagine a black hole, not as an absence, but as a container. Its surface, the event horizon, invisible but real, like the shell of a bubble in space. And on that surface, imagine a kind of cosmic braille, a language so subtle, so compressed, that it stores the story of everything that's fallen in. Not erased, not lost, just folded into the edge. A library written in shadow, a boundary that remembers what space itself forgets. There are few things more humbling than watching a brilliant mind change direction, especially when the shift rewrites how we understand reality itself. For Stephen Hawking, this change didn't come from a sudden epiphany or a dramatic reversal. It came, as many things do in science, from quiet persistence, from the slow, steady tug of contradiction, an itch in the mathematics that wouldn't go away. When Jacob Bekenstein proposed that black holes have entropy, the physics community didn't quite know what to do with it. The idea was elegant, yes, and seemed to solve a puzzle. But it was also deeply unsettling, because entropy implies temperature, and temperature implies radiation. But a black hole was supposed to be the very definition of silent, perfectly black, a place where light goes in and never comes out. Stephen Hawking was one of the skeptics. He believed Bekenstein's reasoning was clever, but ultimately flawed. In Hawking's mind, black holes were classical solutions to Einstein's equations, clean, simple, and one way. They could not radiate. To do so would break the very essence of their definition, and yet something bothered him. In 1974, Hawking began to examine the problem more closely. He looked at it not through the lens of thermodynamics, but through quantum field theory. He wanted to understand what happened to quantum particles near the event horizon of a black hole, and that's when the strangeness began to unfold. In the quantum world, emptiness is never truly empty. Even in a perfect vacuum, tiny fluctuations bubble in and out of existence, pairs of particles and antiparticles that spontaneously appear, then vanish again almost instantly. They are born together and destroy each other, leaving behind no trace. But near a black hole's event horizon, the rules bend. Imagine one of these virtual particle pairs forms just at the edge of the horizon. One particle falls in, the other escapes. Normally these fluctuations cancel out, but in this case the pair is separated. One partner is lost behind the horizon, the other becomes real, slipping away into space. To an outside observer, it looks like the black hole has emitted a particle. And if this keeps happening, and according to the math it does, then over time the black hole begins to lose mass. It radiates. Slowly, imperceptibly, it shrinks. Hawking had found something astonishing. Black holes aren't perfectly black. They glow. The radiation they emit, now called Hawking radiation, is incredibly faint, almost undetectable for any black hole of stellar size. But it's there. A faint, ghostly shimmer. And that shimmer means that black holes have temperature. And if they have temperature, they must have entropy, which means Bekenstein had been right all along. Hawking's calculations gave entropy a precise formula, one that now bears both their names, the Bekenstein-Hawking entropy. It shows that the entropy of a black hole is proportional to the area of its event horizon, not its volume. A square relationship, not a cubic one. This defied intuition, but it matched the mathematics, and suddenly, the edge of a black hole wasn't just a boundary. It was a canvas, a ledger, a screen where the universe kept its secrets. This was more than just a new discovery. It was a revolution. Because if black holes radiate, they are not eternal. They can evaporate. Slowly, yes, over timescales longer than the age of the universe for most, but eventually their mass is converted into energy and lost to space, and that means black holes can die. But what happens to the information that fell in? This is where the tension grows sharp. If Hawking radiation is truly random, if it carries no imprint of what created it, then the information about what fell into the black hole is gone, erased. The radiation does not whisper the story of the object that once collapsed. It doesn't carry the memory of the matter, the arrangement, the entanglement. It simply is, and that, again, violates a fundamental principle of quantum mechanics. Information must be conserved. So we are left with a contradiction, now sharpened to a razor's edge. Quantum theory says that information is eternal. General relativity allows it to vanish. Hawking radiation, born from both theories, seems to suggest that black holes are both thermodynamic objects and quantum paradoxes. Hawking didn't shy away from this conflict. In fact, he embraced it. He was the one who raised the alarm, loudest. He saw the implications of his own calculations and acknowledged the discomfort. The universe, he said, was presenting a mystery deeper than we'd expected. He wasn't alone in this. Other physicists began to explore the consequences. They looked for ways to reconcile the paradox, to find some mechanism, subtle, hidden, elegant, that could preserve the lost information. Some imagined that the information was somehow encoded in the correlations between the radiation particles. Others proposed that it might be stored on the event horizon, waiting to be released in the final moments of evaporation. Still others wondered if our entire understanding of space and time would need to change. But those are questions for later. For now we sit with the quiet wonder of it. Stephen Hawking, once the defender of classical black holes, had become their great reformer. He showed that they glow, that they shrink, that they might one day vanish entirely. And in doing so, he opened a doorway into something stranger than even he could have imagined. A black hole is no longer just a silent sinkhole in space. It is a thermodynamic engine, a quantum furnace, a place where gravity, temperature, entropy, and time weave together into something new. It is not just dark, it is alive. And it is asking us to understand what that truly means. There's something gently counterintuitive about how the universe behaves when you let go of scale. We tend to associate big things with more power, more heat, more danger. A larger fire burns hotter, a bigger sun shines brighter. But in the strange case of black holes, the universe leans in the opposite direction. It whispers a quiet reversal of our instincts, because the smaller the black hole, the hotter it becomes. This idea springs directly from Stephen Hawking's work. When he showed that black holes radiate, he also derived a formula that links their temperature to their mass. And the relationship isn't linear, it's inverse. That means as a black hole loses mass, its temperature rises. This is the opposite of what we might expect from, say, a lump of coal. As it burns away, it cools and disappears. But a black hole, as it radiates and evaporates, grows more intense. The heat builds. The end, far from being a gentle fade into nothing, could be a flash of unimaginable energy. Let's walk through what this means, step by step. For a black hole the size of a star, say 10 times the mass of our sun, its Hawking radiation is minuscule. The temperature is barely above absolute zero. You could surround it with a perfect sensor, and you detect almost nothing. Any warmth it emitted would be dwarfed by the cosmic microwave background, the leftover glow of the Big Bang that still bathes the universe. These black holes are cold, not because they lack energy, but because they're enormous, and that mass keeps their temperature low. But now imagine a smaller black hole, one with the mass of a mountain, or a car, or a grain of sand. As the mass drops, the temperature climbs. At a certain point, the black hole becomes hotter than the universe around it. Its radiation outpaces the energy it absorbs. It enters a runaway state. It begins to evaporate faster, shedding mass more quickly, growing hotter as it shrinks. This is a self-accelerating process. A black hole that's small enough begins to flicker. It boils with quantum light, and in its final moments, if such moments ever come, it may erupt in a final burst of radiation, a last release of energy that says, "I was here," and yet we've never seen this happen. Not because it doesn't occur, but because if it does, it's rare, quiet, and likely lost in the vastness of time and space. Most black holes in the universe are far too massive to reach this stage anytime soon. Their evaporation is measured not in years, but in trillions of years. If any are evaporating now, they are likely the tiniest ones, perhaps born not from stars, but from the chaos of the early universe. These are called primordial black holes. They are purely hypothetical for now, but intriguing nonetheless. The idea is this. Shortly after the Big Bang, the universe was a hot, dense soup of energy and particles. Tiny fluctuations in that chaos, dense pockets of matter and energy, could, under just the right conditions, have collapsed into black holes. Not stellar mass giants, but micro black holes, some no larger than an atom, some smaller still. If they exist, and if they were created in sufficient numbers, then some might still be out there, quietly evaporating. Their hawking radiation would be stronger, their temperatures higher, and their final moments potentially detectable, as brief gamma-ray bursts or high-energy flashes in the dark. Physicists have looked. We've scanned the skies for signs of these events, searched cosmic data for the fingerprint of an evaporating black hole. So far we've found no conclusive evidence, but absence of proof is not proof of absence. The universe is vast. The flashes, if they exist, may be rare or hidden behind noise or happening far beyond our current reach. And yet the idea lingers, because it ties together so many threads. It connects the birth of the universe to the quiet deaths of its strangest objects. It links gravity to temperature, mass to information, beginnings to ends. It gives black holes not just presence, but lifespan. Not just mystery, but change. And it forces us to ask something we're not used to asking of objects defined by silence. What happens at the end? Because if smaller black holes get hotter, and hotter ones evaporate faster, then somewhere, sometime, each one will reach a final stage. A moment where the last remnants of mass vanish. And what that moment looks like, we don't yet know. Does the black hole wink out of existence, quietly and completely? Does it explode, releasing its final energy in a burst of pure radiation? Does it leave behind a remnant, some frozen kernel of information that cannot be erased? Or does the answer lie in a realm we can't yet see, beyond string theory, beyond space-time, beyond our current map? These are not just mathematical questions. They are clues to something deeper, something that touches the structure of the universe itself. Because if we can understand how a black hole ends, we may begin to understand whether anything truly ends at all. The idea that smaller means hotter is just one step along that path. A gentle reversal of our expectations. A reminder that the universe doesn't always scale the way we imagine. Sometimes the tiniest things burn brightest. Sometimes the softest whispers carry the loudest truths. And sometimes in the smallest shadows we find the keys to the largest mysteries. There's something gently counterintuitive about how the universe behaves when you let go of scale. We tend to associate big things with more power, more heat, more danger. A larger fire burns hotter, a bigger sun shines brighter. But in the strange case of black holes, the universe leans in the opposite direction. It whispers a quiet reversal of our instincts. Because the smaller the black hole, the hotter it becomes. This idea springs directly from Stephen Hawking's work. When he showed that black holes radiate, he also derived a formula that links their temperature to their mass. And the relationship isn't linear, it's inverse. That means as a black hole loses mass, its temperature rises. This is the opposite of what we might expect from, say, a lump of coal. As it burns away, it cools and disappears. But a black hole, as it radiates and evaporates, grows more intense. The heat builds. The end, far from being a gentle fade into nothing, could be a flash of unimaginable energy. Let's walk through what this means, step by step. For a black hole the size of a star, say 10 times the mass of our Sun, its Hawking radiation is minuscule. The temperature is barely above absolute zero. You could surround it with a perfect sensor, and you detect almost nothing. Any warmth it emitted would be dwarfed by the cosmic microwave background, the leftover glow of the Big Bang that still bathes the universe. These black holes are cold, not because they lack energy, but because they're enormous and that mass keeps their temperature low. But now imagine a smaller black hole, one with the mass of a mountain, or a car, or a grain of sand. As the mass drops, the temperature climbs. At a certain point, the black hole becomes hotter than the universe around it. Its radiation outpaces the energy it absorbs. It enters a runaway state. It begins to evaporate faster, shedding mass more quickly, growing hotter as it shrinks. This is a self-accelerating process. A black hole that's small enough begins to flicker. It boils with quantum light, and in its final moments, if such moments ever come, it may erupt in a final burst of radiation, a last release of energy that says, "I was here, and yet we've never seen this happen." Not because it doesn't occur, but because if it does, it's rare, quiet, and likely lost in the vastness of time and space. Most black holes in the universe are far too massive to reach this stage anytime soon. Their evaporation is measured not in years, but in trillions of years. If any are evaporating now, they are likely the tiniest ones, perhaps born not from stars but from the chaos of the early universe. These are called primordial black holes. They are purely hypothetical for now, but intriguing nonetheless. The idea is this. Shortly after the Big Bang, the universe was a hot, dense soup of energy and particles. Tiny fluctuations in that chaos, dense pockets of matter and energy, could, under just the right conditions, have collapsed into black holes. Not stellar mass giants, but micro black holes, some no larger than an atom, some smaller still. If they exist, and if they were created in sufficient numbers, then some might still be out there, quietly evaporating. Their Hawking radiation would be stronger, their temperatures higher, and their final moments potentially detectable, as brief gamma-ray bursts or high-energy flashes in the dark. Physicists have looked. We've scanned the skies for signs of these events, searched cosmic data for the fingerprint of an evaporating black hole. So far we've found no conclusive evidence, but absence of proof is not proof of absence. The universe is vast. The flashes, if they exist, may be rare, or hidden behind noise or happening far beyond our current reach. And yet the idea lingers, because it ties together so many threads. It connects the birth of the universe to the quiet deaths of its strangest objects. It links gravity to temperature, mass to information, beginnings to ends. It gives black holes not just presence, but lifespan, not just mystery, but change. And it forces us to ask something we're not used to asking of objects defined by silence. What happens at the end? Because because if smaller black holes get hotter and hotter ones evaporate faster, then somewhere, sometime, each one will reach a final stage, a moment where the last remnants of mass vanish. And what that moment looks like, we don't yet know. Does the black hole wink out of existence quietly and completely? Does it explode, releasing its final energy in a burst of pure radiation? Does it leave behind a remnant, some frozen kernel of information that cannot be erased? Or does the answer lie in a realm we can't yet see, beyond string theory, beyond spacetime, beyond our current map? These are not just mathematical questions. They are clues to something deeper, something that touches the structure of the universe itself. Because if we can understand how a black hole ends, we may begin to understand whether anything truly ends at all. The idea that smaller means hotter is just one step along that path. A gentle reversal of our expectations. A reminder that the universe doesn't always scale the way we imagine. Sometimes the tiniest things burn brightest. Sometimes the softest whispers carry the loudest truths. And sometimes, in the smallest shadows, we find the keys to the largest mysteries. It seems strange to speak of death in the context of a black hole. After all, a black hole is already an ending of sorts. It forms when something collapses past the point of return, when the light dies, the star vanishes, and all paths lead inward. It feels like a final punctuation mark in the sentence of a star's life. But the discovery of Hawking radiation shifted that perspective. It introduced the possibility of another chapter, a kind of slow, spectral afterlife. A new ending that unfolds not with a bang, but with a flickering fade. Black holes, it turns out, do not last forever. If Hawking's calculations are right, then every black hole emits radiation. And while the rate is infinitesimal for large black holes, measured over timescales far beyond anything we can truly imagine, it is still finite. Radiation carries away energy, and energy, according to Einstein's most famous equation, is mass. That means the black hole is shrinking, bit by bit, particle by particle. So the question isn't whether a black hole can die, it's what happens when it does. Let's imagine a lonely black hole, one that has drifted far from the crowded centres of galaxies. It no longer feeds on stars, no gas clouds fall into it, no new mass arrives. Slowly, invisibly, it begins to evaporate. Over billions, then trillions of years, its event horizon shrinks, its temperature rises, the radiation becomes more intense. In the beginning, this process is slow, almost imperceptible, but because the temperature increases as the black hole's mass decreases, the evaporation begins to accelerate. A kind of feedback loop begins. The smaller it gets, the faster it shrinks. The faster it shrinks, the hotter it becomes. Until eventually the process is no longer slow at all. In its final moments, the black hole could shine brighter than it ever did in its entire existence. A brief flash, a burst of high-energy radiation, and then nothing. That, at least, is one possibility. Some theorists suggest that the black hole completely disappears, evaporating into radiation, leaving behind no trace. From the outside, it would appear as though the hole had simply ceased to exist, the curved region of space-time smoothing back into flatness, as if the shadow had folded itself away. But here's where the real mystery begins, because if the black hole vanishes completely, what happens to the information it once contained? This isn't a philosophical question, it's a physical one. According to quantum mechanics, the evolution of a system is unitary, meaning it preserves information. That information might be scrambled, transformed, or spread out, but it cannot be destroyed. The universe doesn't forget. And yet, if a black hole evaporates into purely thermal radiation, random, featureless energy with no memory of what created it, then that principle is violated. This is the information paradox now in its most acute form. It is no longer abstract. no longer confined to thought experiments. It is a direct confrontation between two pillars of modern physics. On one side, general relativity, which says a black hole can fully collapse and vanish, taking everything with it. On the other, quantum mechanics, which insist that cannot be. For decades, this paradox has haunted physicists, not because it hints at something broken, but because it suggests that both theories are incomplete. Each works brilliantly in its own realm, relativity for the vast, quantum mechanics for the small. But at the boundary of a black hole, those realms collide, and the result is confusion. Different proposals have been offered. Some suggest that the Hawking radiation is not truly random, but subtly entangled with the information inside the black hole. That over time, as the black hole evaporates, those entanglements reveal the story of what fell in. If that's true, then information is not lost. It's just disguised in correlations too subtle to detect. Others propose that information is somehow stored on the event horizon itself, a two-dimensional imprint of a three-dimensional history, a kind of cosmic skin that remembers everything, even as the interior collapses. Still others suggest that the final moments of black hole evaporation are governed by new physics, perhaps from string theory or quantum gravity, where the singularity is resolved and information is preserved in ways we can't yet describe. There's even the idea of black hole remnants, tiny, stable objects left behind after evaporation, containing the compressed history of everything the black hole once consumed. These remnants would be small, dense, and possibly undetectable, but they would preserve unitarity. The truth is, we don't yet know. We don't have the instruments to watch a black hole evaporate. We don't know what laws apply at the smallest scales of space-time. We're standing at the edge of our understanding, staring into a region that resists our tools. But this is not a failure. It's a beacon. Because every time we find a contradiction like this, every time two great theories disagree, we know we are close to something profound, something new, something that might unify the language of the cosmos. The information paradox isn't just a problem, it's a map. It tells us where to look, where gravity and quantum entanglement meet, where time unravels, where space might not be what it seems, where the future of physics is waiting to be born. And so the death of a black hole is not just an end, it's a question with no clear answer, but one that carries within it the shape of our greatest hopes, that the universe is knowable, that information matters, that even in the deepest silence something speaks, and maybe, just maybe, that whisper is telling us that nothing is ever truly lost. If you ever find yourself wondering why scientists argue so passionately about something as intangible as a black hole, it helps to understand what's really at stake. This isn't just about whether a thing in space glows or vanishes. This is about whether the universe remembers what happened inside it, or forgets entirely. And physics, as strange and uncertain as it often seems, has rules about memory. One of the most fundamental is something called unitarity. It's a core principle of quantum mechanics, and it simply means this: information cannot be destroyed. In a quantum world, every process, no matter how chaotic or strange, must be reversible in principle. If you had perfect knowledge, you could rewind the clock and reconstruct what came before. Particles may scatter, entangle, and spread across the cosmos, but nothing vanishes without a trace. The universe plays fair, it keeps its ledgers tidy. There are no true erasures, only rearrangements. This is not a philosophical preference. It's built into the mathematics of quantum mechanics. If unitarity fails, then so does the entire predictive structure of the theory. The future wouldn't follow from the past. Probability would no longer add up to 1. The whole framework would begin to unravel, which brings us back to the black hole. According to Stephen Hawking's calculations, black holes emit thermal radiation, meaning it's completely random. It carries no information about what formed the black hole or what fell into it. It's It's as though the universe was slowly leaking anonymous heat into the void, shedding mass without memory. And when the black hole finishes evaporating, you're left with a warm, empty patch of space. But the information, the detailed record of everything that entered, seems to be gone. And that's the problem. Because if the radiation is truly random, then quantum information has been destroyed. And that's not allowed. This is the heart of the black hole information paradox. A contradiction between two towering theories of physics. On one side, general relativity, which describes gravity and the fabric of space-time, and which allows black holes to erase the past. On the other, quantum mechanics, which governs particles and interactions, and which insist that no such erasure can occur. Both are exquisitely precise. Both have passed every test. And yet, they cannot both be right here. Something has to give. It's not just a disagreement between two branches of physics, it's a deep question about reality itself. Think of it like this. Imagine throwing a diary into a fire. The pages curl, the ink smokes, and eventually all you see is flame. From a classical perspective, the information is lost, but from a quantum perspective, the molecules, photons, and ash still contain, in principle, the full record, just scattered and nearly impossible to reassemble. But now imagine throwing that diary into a black hole. You don't see fire, you don't get ash. All you see is a brief distortion in space-time, and then nothing. The hole grows slightly, its surface area increases, it radiates a little faster, but when it finishes evaporating there's no smoke, no fragments, no chance of reassembly. The diary isn't scrambled, it's gone. And this unsettles physicists to their core, because it suggests that black holes do more than hide information, they delete it. They overwrite the past, not just in practice, but in principle. That would mean the laws of physics are not reversible, that the universe is not a perfect record, and that, deep down, the future may not depend fully on the past. It's a crack in the foundation. Which is why the black hole information paradox is not just a problem for astrophysicists. It's a crisis for all of physics. It touches quantum field theory, thermodynamics, string theory, quantum gravity, and even the philosophy of time. It forces physicists to ask, what is information really? Is it a thing, a quantity, a pattern, a boundary, and where does it live? And for decades, there was no satisfying answer. Some tried to deny the problem, insisting the rules of black holes must be subtly different. Others argued that perhaps quantum mechanics itself was flawed, that unitarity might not be sacred after all. A few dared to suggest that when we finally unify quantum theory with gravity, the paradox will dissolve like mist. But none of that resolved the discomfort, because even if we can't yet see it happen, even if the final stages of evaporation lie far beyond our reach, the mathematics insists we face the contradiction. The black hole sits quietly, radiating into darkness, its mass dwindling, its glow rising. And behind it all, the universe asks, where did the story go? Every field has its great debates, moments when the best minds in the world stand on opposite shores of a question, sending arguments across like carefully folded paper boats. In the world of black holes, one such debate became so central, so personal, and so persistent that it earned a dramatic name, the Black Hole War. At its core, this was a war of beliefs about the universe, not just equations. On one side stood Stephen Hawking, who, based on his own calculations, firmly believed that information was lost in black holes. On the other was Leonard Susskind, a theoretical physicist who had spent years wrestling with quantum field theory and string theory. For Susskind, the idea that information could be destroyed was unacceptable. It wasn't just inconvenient, it was catastrophic. What made this debate so compelling wasn't just the personalities involved, though they were certainly brilliant and stubborn in equal measure. It was the clarity of the disagreement and the high stakes behind it. If Hawking was right and black holes destroyed information, then quantum mechanics itself needed to be revised. Unitarity, this bedrock principle that the evolution of quantum systems is reversible, would fall apart. The very idea that the universe keeps track of its own history would be a comforting illusion. Physics would become unpredictable, not because we lacked data, but because the data had truly ceased to exist. But if Susskind was right, and information was preserved, then Hawking's model of black hole evaporation had to be missing something. Perhaps the radiation wasn't truly random. Perhaps the event horizon somehow encoded the data. Or perhaps black holes weren't what they seemed to be at all. The black hole war wasn't fought with telescopes or laboratories. It was fought in chalk dust and lecture halls, through papers, conferences, and late-night emails. It wasn't a single skirmish, but a prolonged siege, years of back-and-forth thought experiments and paradoxes refined to sharper and sharper edges. One of the key battlegrounds was the concept of the no-hair theorem. This idea, central to general relativity, states that black holes are entirely characterized by just three properties: mass, spin, and charge. They have no hair, no extra features, no textures, no hidden wrinkles that could encode detailed information about what fell in. From the outside, every black hole with the same three numbers looks the same, but Susskind challenged this. He suggested that the event horizon itself might store information not in a literal pile, but in a subtle quantum mechanical way. Like a hologram or a ripple on a pond, the black hole's surface might reflect, however faintly, the history of its contents. This idea wasn't entirely new, but Susskind gave it new urgency. He called it black hole complementarity, a principle we'll explore more deeply later. For now, the key point is this. Susskind argued that the paradox of information loss might not come from a flaw in the laws of physics, but from a misunderstanding about perspective. From the outside, the black hole absorbs matter, grows and radiates. From the inside, an object falls smoothly toward the singularity. Both views are consistent within their own frames of reference, and because no observer can experience both simultaneously, the contradiction might only be apparent. Hawking pushed back, of course. He didn't deny the strangeness of the paradox, but he remained convinced that information was gone. He believed that no mechanism, no encoding, no hidden structure could account for the complete preservation of quantum data. His radiation was random. His model was elegant, but it carried a cost. And then something shifted. As more physicists weighed in, as arguments evolved, as ideas like holography and entanglement entropy began to gain traction, the tide began to turn. Hawking, famously, cautious but never rigid, began to reconsider. In 2004, nearly 30 years after first proposing the information loss paradox, he announced that he had changed his mind. In a presentation at a scientific conference, he stated that information was not destroyed by black holes after all. He had been wrong. The universe, he now believed, did preserve its history. The radiation, he conceded, must somehow carry the encoded data, however subtly, however scrambled. The moment was more than scientific. It was human. A brilliant physicist, once at the centre of a profound contradiction, had allowed the evidence, the community, and the evolving theories to move him, not with defeat, but with grace. Susskind, in later writings, described this not as a victory but as a reconciliation. The war had been fought not to vanquish an opponent, but to uncover a deeper truth. The disagreement, fierce though it was, had been a gift, a way to sharpen understanding and drive the field forward. And that's often how science works. Not through certainty, but through struggle. Not through answers, but through the refinement of better questions. The black hole war didn't give us a complete solution. It didn't resolve every tension between gravity and quantum mechanics, but it reshaped how we asked the question. It introduced new ideas, like holography and entanglement, that would define the next era of theoretical physics. And it reminded us that even the darkest regions of space can illuminate what we believe about time, memory, and truth. A black hole is not just a challenge to observation, it's a challenge to coherence, to the idea that the universe can be told as a single, seamless story. And yet, in that challenge, something beautiful emerges, not an answer, but a bridge. Sometimes, a paradox doesn't go away just because people stop arguing. It evolves. It takes on new forms guided by fresh insight and unfamiliar language. In the case of black holes and information, the next chapter didn't come with the clash of titans. It arrived more quietly, from a physicist named Don Page, a student of Stephen Hawking, and someone who deeply admired his mentor's work. But admiration never stopped science from asking hard questions. Don Page proposed a way to measure the problem, to put structure around the mystery. If information really was preserved, if black holes didn't destroy their histories, then that preservation should leave a pattern in the radiation, not just in theory, but in how entropy behaves over time. Now, entropy is often thought of as disorder, but in quantum terms it's more subtle. In this context, it's a measure of entanglement. How much information is shared between two systems, even when they're separated. When you look at a black hole evaporating, the question becomes, how entangled is the outgoing radiation with whatever remains inside? Page's insight was to track the entropy of Hawking radiation as the black hole evaporates. At the start of the evaporation, the radiation is nearly random. There's no information encoded in it, just featureless heat. So the entropy of the radiation increases steadily. More randomness, more disorder. But that can't continue forever, because if information is preserved, then eventually the radiation must begin to carry some imprint of the black hole's past. The entropy should peak, then decline, reflecting a transition from pure randomness to meaningful structure. This creates a shape, a curve, that now bears Don Page's name, the Page curve. On a graph, it looks almost gentle, a slow rise, a graceful peak, and a soft fall. But that curve has enormous consequences. It tells you that information is not lost, it's just delayed, hidden at first, then released. The black hole doesn't destroy memory, it just takes its time returning it. The key moment in this process is called the Page time, the point halfway through evaporation when the radiation starts to become less random and more informative. Before this point, the entropy increases, afterward it decreases, and at the very end, if information is fully recovered, the entropy of the radiation drops to zero. But how? How does random radiation begin to carry meaning? This is where entanglement becomes crucial. In quantum mechanics, entanglement is a link, a kind of invisible thread connecting two particles such that the state of one reflects the state of the other, no matter how far apart they are. It's not magic, it's structure, it's coherence, it's a shared story that no single piece reveals, but that becomes clear when you hold both ends. When black holes radiate, the outgoing particles are believed to be entangled with what's inside. Early in the evaporation process, these connections are strong. The outside world receives fragments, echoes, but the full picture remains behind the horizon. But as the black hole shrinks and more radiation escapes, something begins to shift. The later particles are not just entangled with the interior, but also with each other. Patterns form across the radiation stream. Connections stretch outward. The story begins to assemble itself not in the black hole, but in the radiation itself. If this view is right, then Hawking's original calculation, while brilliant, missed something fundamental. He treated each piece of radiation as independent, random. But quantum entanglement weaves those pieces into a tapestry. It doesn't change the math of any one photon, it changes the meaning of the whole. This understanding has grown stronger in recent years, especially with insights from quantum information theory. Physicists now analyse black holes not just as gravitational objects, but as processors of quantum data. You can think of them, metaphorically, as information transformers. They take in complex systems, scramble them, delay their return, and then slowly radiate the encoded results, like a cosmic slow cooker of secrets, and the page curve provides the recipe. It tells us what the output should look like if unitarity holds. Of course, we haven't observed this directly. The radiation from real black holes is far too faint to measure, but theoretical models, simulations, and analogues in quantum systems all suggest that something like the page curve is not only possible, but necessary for a universe that preserves information. It's not proof, but it's a map, and it makes a radical claim in the quietest way. That black holes don't forget. They delay, they distort, they stretch time and compress memory, but they still somehow obey the rules. Even when space folds in on itself, even when light cannot escape, the page curve doesn't scream, it doesn't declare victory, it just arcs, like the shape of a life, like a breath held, then slowly released. It suggests that even the darkest processes in the universe follow a hidden symmetry, one where loss becomes recovery, where entropy bends but doesn't break, where meaning waits patiently behind randomness, humming softly in the background. And in that curve, we see a kind of promise that the universe may be strange but not cruel, that memory may bend but not vanish, that even when we throw something into the dark, the echoes can still find their way back. There's a quiet trick the universe plays, one that only becomes obvious when we stare at the edge of black holes. It's the kind of trick that doesn't rely on illusion or sleight of hand, but on something deeper, on perspective, on the possibility that two seemingly contradictory descriptions of the same event can both be true, so long as they are never experienced at the same time. This idea is called black hole complementarity, and it might be the gentlest resolution to one of the fiercest paradoxes in theoretical physics. It begins with a simple, unnerving question. What happens to someone who falls into a black hole? Let's say, just for the sake of imagination, that you decide to drift toward the event horizon. From your point of view, the journey would seem almost unremarkable. The closer you get, the stronger gravity pulls, yes, but according to Einstein's theory of relativity, if the black hole is large enough, you might not even notice crossing the boundary. No wall, no flash, just a smooth glide into deeper curvature. Once you pass the event horizon, your fate is sealed, but the crossing itself might feel ordinary. But now, picture your friend watching you from far away. To them, something very different is happening. As you approach the horizon, time seems to stretch. Your movements slow. Light from your body becomes redder and dimmer, fading into infrared, then radio waves, until it vanishes entirely. From their perspective, you never quite cross the horizon. You hover, frozen in place, your final image forever trapped at the edge, like a photograph pinned to spacetime. Two experiences, one object, no contradiction, until we try to merge them. Because if you fall in and vanish, but your friend sees you frozen at the edge, then where are you? Are you inside the black hole, tumbling toward the singularity? Or are you smeared across the horizon, encoded as a kind of surface memory? Black hole complementarity says, both. Not in a vague mystical sense, but in a very precise technical way. The laws of physics allow both descriptions to be valid, but only from within their own reference frames. You cannot experience both. You cannot be both observer and falling traveller. The contradiction arises only when you try to stitch together two perspectives that, in practice, can never communicate. To the outside observer, the black hole's surface acts like a storage device. Information about everything that falls in is encoded there, compressed, scrambled, but not destroyed. Over time, that information is slowly released through Hawking radiation. From this view, the black hole is a kind of cosmic hard drive, slowly uploading its contents back into the universe. But from the falling observer's frame, the internal story, you simply pass through the horizon and descend toward the singularity, where presumably your fate is sealed. The interior has no record of surface encodings, no awareness of Hawking radiation. It's a different narrative, unfolding in a different domain. Complementarity doesn't try to merge these into one unified picture. Instead, it says, physics works best when told locally. That is, each observer's story is self-consistent, and the universe ensures that no observer can compare notes in a way that breaks the illusion. In other words, the contradiction is global, not local. It only appears if you try to take God's eye view, an impossible synthesis of inside and out. But the universe doesn't require such omniscience. It's content with a patchwork of perspectives, each stitched into the fabric of its own experience. And this isn't the first time physics has taught us this lesson. In quantum mechanics, we're used to complementarity in the form of wave-particle duality. Light behaves like a wave in some experiments, like a particle in others. You cannot observe both behaviours simultaneously. Which one you see depends on how you look. The truth isn't either or, it's both, depending on the context. Black hole complementarity is like that, but on a cosmic scale. It tells us that the universe may not provide a single, objective narrative that satisfies all observers at once. Instead, it offers coherent stories from distinct vantage points, and carefully arranges things so that no observer can catch the overlap. It's a subtle solution, and some physicists are uneasy with its implications. It challenges our desire for a single, seamless reality. It forces us to accept that the truth may be observer-dependent, not because reality is subjective, but because information itself is woven into space-time in a relational way. And yet, this idea has power. It preserves unitarity. It allows for information conservation. It gives meaning to Hawking radiation without erasing the experience of falling in. It suggests that the paradox of black holes is not a violation, but a misunderstanding, an attempt to ask a question that the universe is too polite to answer all at once. And perhaps that's the point. Perhaps reality isn't a smooth scroll, but a tapestry of overlapping fragments. Each thread is consistent. Each observer's view is valid. And when you try to see the whole picture from above, the threads twist, and the pattern blurs, but the structure still holds. Complementarity doesn't solve every mystery, but it offers something just as valuable, a way to live with contradiction, a way to accept that the universe may not be designed for us to see all of it at once. That understanding may come not from unifying all perspectives, but from learning how they coexist. One story from the outside, one story from within, both true, neither complete. And the boundary between them, the event horizon, is not just a surface in space. It's a reminder that the edge of what we can know is also the beginning of wonder. There's something quietly unsettling about a surface. It looks like the end of something, a barrier, a boundary, the final edge beyond which nothing more exists. We tend to think of depth as where the truth lives. To find answers, we dig, we peer inside, we go inward. But when it comes to black holes, and perhaps even to the universe itself, the answers might not be hidden within. They might be waiting on the surface. It all begins with a strange observation, one that Jacob Bekenstein made long ago and that Stephen Hawking reluctantly confirmed. A black hole's entropy doesn't scale with the volume of space it encloses. It scales with the area of its event horizon, the outer shell, the boundary between what can be seen and what cannot. This is not what anyone expected. Most systems in physics, clouds of gas, containers of water, even entire galaxies, have entropy that scales with volume. The more room you have, the more complexity you can hide inside. But a black hole doesn't follow that rule. Its capacity to hold information grows only with the size of its surface, and the more this idea was explored, the more profound it seemed. If a black hole's entropy is a measure of how much information it contains, and if that information scales only with surface area, then something remarkable might be true. Everything that has ever fallen into a black hole, every star, every atom, every quantum twist of energy, it's all still there. Not lost inside, not collapsed into a singularity, but somehow encoded on the surface. Not like objects in a box, but like patterns in a shell. As if the skin remembers what the core forgets. And so the question quietly emerged. If a black hole can store the entire memory of its interior on its horizon, why stop at black holes? What if this isn't a special feature of collapsed stars, but a general principle of the universe? What if space itself, the air between planets, the void between galaxies, even the volume you inhabit now, is not the deepest part of reality? What if everything we think of as existing in 3 dimensions is really just a reflection, an emergent shadow of something more fundamental, written on a 2-dimensional surface we can't directly see? This is the essence of the holographic principle, a startling proposal that the universe may be like a cosmic hologram, not in the sense of being unreal or projected by machines, but in a deeply physical, mathematical sense. In a hologram, every piece of the surface holds a record of the whole. The 3-dimensional image you perceive is created by interference patterns stored on a flat sheet. There's no real depth, only the illusion of it, conjured from data stored on a boundary. The holographic principle suggests the universe might work the same way. The idea is not purely speculative. It was sharpened into something mathematically precise in the late 1990s, when physicist Juan Maldazzina proposed a model that took this wild idea and gave it a concrete form. In a particular kind of curved universe, called anti-de Sitter space, or ADS for short, Maldazzina showed that the behaviour of gravity and matter inside the volume could be exactly mirrored by a non-gravitational theory on the boundary. This correspondence is now called ADS CFT duality, and it's one of the most studied concepts in modern theoretical physics. At first, it sounds too strange to be true. A universe with gravity, black holes and curved space-time being described completely by a theory with no gravity, living on a flat surface at the edge. But the math works. Every particle interaction inside the bulk, every twist of curvature, has a precise counterpart on the boundary. 2 descriptions, 1 reality. And if this is true in one kind of universe, perhaps it is true, or at least partially true, in ours. This would explain so much. It would help resolve the black hole information paradox, because if the information never really entered the black hole's volume, but was always encoded on the surface, then it was never truly lost. Hawking's radiation then is not random noise, but a gradual unpacking of boundary data. The black hole evaporates, and in doing so, releases its story, not from the singularity, but from the skin. But more than that, it reimagines what space itself is. We usually think of space as a container, something things live inside. But in this view, space is not fundamental. It is emergent. It arises from relationships between quantum states, from the way information is entangled and organised. Volume is not a stage on which physics happens. It is a byproduct of information structure. The implications stretch far beyond black holes. If the holographic principle is real, then gravity itself might not be a fundamental force. It might be the result of entanglement. Curved space-time might be what happens when information is organised in a particular way. Mass, motion, even time could be secondary to a deeper informational reality. It's a poetic inversion. We look for truth in the depths, but the surface may be the script. Black holes, then, were not errors in the system. They were clues. They forced us to look at boundaries, to notice where the equations bent, and in doing so they whispered something quietly revolutionary. Perhaps the edge is the origin. Of course, these ideas are still evolving. The holographic principle is not a final answer. It's a lens, a new way of seeing. And like all good lenses, it clarifies some things while blurring others. But what it offers is more than elegance. It offers hope. Hope that the paradox wasn't a failure of physics, but a sign that we were asking the wrong question. Hope that even the most mysterious objects in the universe follow laws. Hope that the universe, while strange, is still kind enough to remember. There's something quietly magical about mirrors. They reflect light, of course, but they also reflect assumptions. We look into them and expect a faithful image, a world flipped sideways but otherwise intact. But if you could step into the reflection, live on that surface, what rules would govern your existence there? Would the world be simpler, flatter, or would it hold secrets deeper than the image it reflects? Physicists don't often work with literal mirrors, but the idea of duality, a reality expressed in two very different languages, is something they've come to embrace with cautious wonder. In the case of black holes, that duality takes its most famous and mathematical form in what's called the ADS CFT correspondence, proposed by Juan Maldacena in 1997. At first glance, it's just a collection of initials, ADS for anti-de Sitter space, CFT for conformal field theory, but underneath those letters lies a revolutionary idea that a universe with gravity, curvature, and black holes can be fully described by a lower dimensional theory with no gravity at all, living on the boundary. It sounds like the setup for a riddle. How can a flat theory with no gravity know anything about a curved world where gravity reigns supreme? And yet, mathematically, it works. Not just as an approximation, but as a complete duality. A one-to-one correspondence between everything that happens inside the volume and everything written on the surface. Let's pause here and break this down gently. Imagine a snow globe. Inside, there's a whole world, swirling particles, tiny buildings, curves of glass. You might think to understand the interior, you'd need to study it directly, but in the ADS CFT model, everything happening inside the globe can be described by equations etched along the outer shell. The interior and exterior speak different dialects, but they tell the same story. The ADS part refers to a specific kind of space, anti-de Sitter space. It's not the shape of our own universe, which appears to be flat or slightly curved in the opposite direction, but it's a space with elegant mathematical properties, the kind that let physicists test deep ideas about gravity and quantum theory in a controlled sandbox. In ADS space, the geometry naturally includes a boundary, an edge you can do physics on. The CFT side lives on that edge. It's a quantum field theory, like the ones that describe particle physics, electromagnetism, and the other forces that aren't gravity. In this theory, particles interact, waves propagate, and entanglements form. There's no notion of space bending, no singularities, no black holes in the traditional sense. And yet, for every black hole in the ADS interior, there is a corresponding state in the boundary theory. For every gravitational interaction, there is a pattern of entanglement. It's not an analogy, it's an equivalence. To say that the ADS universe is holographic is to say that the CFT encodes everything about it. The shape of space-time, the motion of stars, the thermodynamics of black holes. It's all there, hidden in the structure of quantum fields stitched along the edge. This might sound abstract, and it is, but it offers a profound way to understand the black hole information paradox. Because if the interior of a black hole, including everything it has ever consumed, is just a reflection of patterns on the surface, then information never enters the volume in the way we thought. It's always been part of the boundary theory. The process of black hole evaporation, then, is not the disappearance of data into a singularity. It's the evolution of a boundary system. Information doesn't fall in. It rearranges itself on the skin. In this view, gravity is not a fundamental force, but an emergent one, something that arises when the boundary system behaves in certain ways. This is one of the most startling ideas in modern physics, that the curves of space-time, the warps and folds that guide planets and light, might simply be shadows cast by deeper, flat processes. You don't need to dig into the bulk to find answers, you can read the surface. This approach also offers a new way to understand entanglement. In the boundary theory, entangled particles shape the correlations across space. The more entangled the parts of the boundary are, the more connected the corresponding points in the interior become. It's almost as if space itself is stitched together by entanglement. Tear the entanglement and the geometry breaks, strengthen it, and distance shortens. This leads to an even bolder idea, that space-time itself is built from quantum information, not just metaphorically, but literally. Geometry becomes a language written in the alphabet of entanglement. Curvature becomes a conversation among bits, and again, it was black holes that first revealed this secret. They demanded that we explain how surface entropy could encode interior complexity. They insisted that radiation carry memory. They drove us, paradox by paradox, to the edge of space, and asked, what if this edge is the whole story? ADS CFT gives us a tool. It doesn't answer every question. Our universe is not exactly ADS after all. But it offers a model, a map, a direction. And like all good maps, it reshapes how we see the terrain. Not as a smooth, continuous expanse, but as a projection, a relationship, a web. So we returned to the mirror. We thought we were looking through it, into depth, into truth. But perhaps we've only been looking at it. And now we see that the reflection holds all the meaning we need. Maybe we don't live inside the universe, but on its edge. Maybe gravity is not the force that pulls things in, but the story that emerges when enough pieces hold hands. And maybe, in the flickering light of a black hole, the surface has always been telling us the truth. We just had to learn how to listen. The deeper you go into the black hole paradox, the more it begins to feel like standing in front of a locked door with dozens of keys, each beautifully crafted, each turning just a little, none quite opening the way. Some theories offer elegant mathematics, others provide poetic metaphors, but one approach, in particular, has long promised to be more than a metaphor, to go beyond suggestion and actually count the hidden things inside. That approach is string theory. String theory began, decades ago, not as a theory of black holes, but of tiny vibrating filaments, strings so small they make atoms look enormous by comparison. These strings weren't particles in the traditional sense. They were one-dimensional objects, whose different vibrational modes gave rise to all known particles and forces. Gravity emerged naturally from one such vibration. Space, time and matter became not separate entities, but different expressions of the same fundamental language. It was ambitious. It still is. And while string theory is often described as a candidate for a theory of everything, that phrase may obscure the quiet power it has brought to specific, thorny problems, like the question of what lies inside a black hole. In 1996, physicists Andrew Strominger and Kumran Vafa made a remarkable breakthrough. Working within a version of string theory involving extra dimensions and mathematical symmetries, they found a way to count the number of quantum states, or microstates, that a certain kind of black hole could have. This wasn't just a guess or a vague gesture, it was an actual calculation. They constructed a model of a black hole using objects called D-branes, which are surfaces where strings can attach. In this setup, the black hole wasn't a smooth, featureless region of warped space-time. It was a highly complex configuration of strings and branes, each arrangement representing a different microstate. And when they added up the number of possible configurations, something astonishing happened. The result matched exactly with the entropy predicted by Bekenstein and Hawking. Not approximately, not roughly. Exactly. The number of distinct string configurations corresponded to the amount of information the black hole's event horizon could store. For the first time, entropy was not just a mysterious measure of hidden stuff. It was a count of actual internal structures, even if those structures were invisible from the outside. This was a profound moment. It suggested that black holes are not truly bald, that beneath the apparent simplicity of the no-hair theorem, there is a rich internal landscape, a seething, tangled geometry of strings, vibrating and intertwining in dimensions we cannot see. But there was a catch. The result was derived for a very specific type of black hole, one that exists in a universe with supersymmetry and extra spatial dimensions. It relied on certain simplifications, like the black hole being extremal, having the smallest possible mass for its charge, and being static, not rotating or evolving in time. Still, it showed that microstates were not just a theoretical wish. They were countable, and that, in principle, black hole entropy could be understood from the inside out. This gave birth to the idea of fuzzballs. In traditional general relativity, a black hole's interior collapses to a singularity, a point of infinite density, where known physics breaks down. But in the fuzzball proposal, the singularity is replaced by a tangle of string-theoretic microstates. Each fuzzball is different, depending on the precise arrangement of strings and brains. There is no single interior, no uniform solution. Instead, each black hole is a unique quantum object, whose individuality is smeared across a fuzz of possibilities. To an outside observer, these microstates might all look the same. The event horizon smooths over the details, but the Hawking radiation they emit could, in theory, reflect subtle differences, allowing information to leak out slowly and precisely as the black hole evaporates. The fuzzball model is still being developed, and it's not without controversy. It's challenging to extend it to the kinds of black holes we observe in our universe. Messy, rotating, non-extremal beasts formed from collapsing stars. But it provides something essential, a physical, calculable structure inside the black hole. Not just metaphors, not just boundaries and dualities, a genuine granular interior, and it speaks to a broader truth, that simplicity on the outside does not imply simplicity within. A black hole may be defined by three numbers, mass, charge, and spin, but that doesn't mean it's empty. It may mean the reverse, that its complexity is compressed, not erased, that its identity is hidden, not lost, that, like a sealed book, it holds stories too densely packed to be read from the cover alone. String theory offers the tools to try and read those stories, to imagine the black hole not as a featureless void, but as a canvas painted with vibrational possibilities, every colour, every twist, every note coded into a surface we cannot yet reach. And even if the theory remains incomplete, even if we never measure those strings directly, it reminds us that there is structure beneath the silence, that the things we call unknowable may only be waiting for a new language, that even in the darkest corners of space, complexity persists, not to confuse, but to remember. For a while it seemed as though the pieces were starting to fit. The holographic principle, ADS CFT duality, string theory microstates, these were not complete answers, but they were elegant frameworks. They pointed toward a universe where information was never truly lost, only scrambled and redistributed in ways we were just beginning to understand. The paradox of the black hole was being untangled, strand by quantum strand. And then, almost as if the cosmos couldn't resist one last twist, a new contradiction appeared. This one wasn't old and dusty, like those birthed from Newton or Einstein. It was sharp, recent, and unsettling. It came not from the depths of a telescope, but from the quiet collision of equations on a chalkboard. In 2012, a group of physicists, Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, published a paper that would reignite the fire. They proposed what has come to be called the EMPS paradox, or more provocatively, the firewall paradox. At first, it sounds almost like a thought experiment gone too far. What if the event horizon of a black hole isn't smooth and silent, but a wall of searing energy? Not a gentle passage into darkness, but a violent, fiery boundary that burns anything that tries to cross. It contradicts everything general relativity tells us. Einstein's theory insists that for a sufficiently large black hole, crossing the event horizon should feel like nothing at all. You wouldn't even notice. The curvature of space becomes strong, yes, but the local physics remain smooth. The drama lies in the future, near the singularity, not at the horizon itself. But the AMPS argument says that can't be right, not if unitarity is preserved. To understand why, we need to revisit something deceptively simple: entanglement. Remember, when a black hole emits Hawking radiation, that radiation is initially entangled with the interior of the black hole. That's fine, but as time goes on, and especially after the page time, when the black hole has emitted more than half of its original entropy, newly emitted particles must also be entangled with the earlier radiation in order to preserve unitarity. Now here's the problem. A single quantum system cannot be maximally entangled with two independent systems at once. It's called the monogamy of entanglement, a fundamental rule in quantum mechanics. You can't give your full secrets to two friends at once, so when a new Hawking particle appears at the horizon, it faces a contradiction. If it's entangled with both the black hole interior and with earlier radiation, something must give. Either 1. It's not entangled with the interior, meaning the smooth, gentle space-time of general relativity near the horizon must break down. A firewall forms, the horizon becomes violent. 2. Or it's not entangled with the earlier radiation, meaning information is lost. Unitarity is violated. 3. Or maybe quantum field theory itself needs rewriting in this regime, introducing new physics we haven't yet imagined. It's an impossible trilemma. Pick any two, and you must abandon the third. And none of the three options is comfortable. If the firewall is real, then general relativity fails in a regime where it has always worked. The very idea that a black hole has a smooth horizon, that space-time continues inward, becomes false. The event horizon becomes a catastrophic boundary, a wall of energy where reality itself disintegrates. This contradicts not just theory, but everything we've come to believe about how gravity behaves near large black holes. If unitarity fails, then information is lost after all, bringing us full circle back to Hawking's original dilemma, and forcing us to abandon the foundational principles of quantum mechanics. And if quantum field theory breaks down, we're left without a clear guide to what replaces it. The result is a crisis not of data, but of frameworks. The paradox sharpens. The language we use to describe reality, quantum mechanics, general relativity, entanglement, begins to speak in contradictory tones. Physicists responded to the firewall paradox with a mixture of fascination and unease. Some embraced it, suggesting that firewalls might indeed form, perhaps through violent quantum fluctuations. Others rejected it outright, arguing that it misunderstood the nature of information or entanglement in curved space. Still others looked for more subtle ways out, invoking ideas from quantum error correction, holographic encoding, or even the notion that space and time themselves might be emergent from more fundamental patterns. A particularly poetic response came from those who favoured complementarity. They suggested that the firewall might exist for one observer but not another, that contradictions arise only when we try to force incompatible perspectives into a single frame. Perhaps the infalling observer sees a smooth horizon, while the distant observer sees a firewall, but no one can observe both. The paradox, once again, might live in the story, not in the physics. But unlike older paradoxes, the firewall won't fade quietly. It continues to challenge assumptions on both sides of the theoretical divide. It reminds us that resolution is not always closure, that sometimes, in physics, as in dreams, the closer you look, the more the floor bends beneath your feet. What lies at the edge of a black hole? A smooth passage? A tangled web? A wall of fire? We don't know, and that's the honest answer. But in the discomfort lies something essential. Black holes are not just celestial objects. They are the boundary between what we know and what we can't yet describe. They are where physics tests its faith, where equations stammer, and where certainty pauses to catch its breath. We wanted them to be answers, They turned out to be questions that burn. At this point in the story, it would be natural to feel a little disoriented. The black hole, which once seemed like a final punctuation mark in the sentence of physics, now reads more like a complex metaphor with footnotes written in multiple languages. We've gone from event horizons to entropy, from radiation to holograms, from smooth geometry to possible firewalls, and still the question echoes. Where does the information go? Perhaps the answer, like so many things in theoretical physics, lies not in the facts we already know, but in the connections we haven't yet fully understood. In 2013, just a year after the firewall paradox reignited tensions, two of the most powerful symbols in physics, wormholes and entanglement, were proposed to be the same thing. Not metaphorically, not poetically, literally. This idea is known as EPR. The equation is compact, almost cryptic. But behind those 6 characters lies a sweeping claim that Einstein-Rosen bridges, commonly called wormholes, and Einstein-Podolsky-Rosen entanglement, a cornerstone of quantum physics, are 2 descriptions of a single, deeper phenomenon. On one side of the equation, we have ER, referring to wormholes. These are hypothetical tunnels in spacetime, first proposed by Einstein and Rosen in 1935. They link 2 regions of the universe through a shortcut, a throat that curves through an extra dimension. In most classical models, wormholes are unstable or non-traversable. They are mathematical curiosities, not practical pathways. But they capture our imagination because they suggest the possibility of connection through space without crossing it. On the other side, we have EPR, also from 1935, representing quantum entanglement. When 2 particles are entangled, their states are linked. Measure one, and you instantly know something about the other, no matter how far apart they are. It's not that information travels faster than light, it's that the 2 particles are described by a shared quantum state. They are one system, stretched across space. The bold idea behind EPR is that every instance of entanglement corresponds to a microscopic wormhole, that the connection between 2 particles is not just informational, but geometrical. That entanglement doesn't just affect what we know about the world, it affects the shape of space itself. At first, this might sound like science fiction, but in the context of black holes, it begins to offer something profoundly useful. Remember the challenge. As a black hole evaporates, information appears to escape. But how does it get out? If the event horizon is smooth, how can outgoing radiation become entangled with interior information and earlier radiation without violating the rules of quantum theory? Now imagine that each bit of Hawking radiation is not simply flying away, isolated and random, but is instead entangled with a partner particle still inside the black hole. And that entanglement forms a kind of bridge, a wormhole, invisible, infinitesimal, but real in the sense that it reflects the underlying geometry of entanglement. In this picture, the Hawking radiation doesn't just drift off meaninglessly, it stays connected to its source via the strange fabric of entanglement-shaped space, and as more radiation escapes, the pattern of these connections might grow. At a certain point, the structure becomes rich enough that the information encoded inside the black hole becomes recoverable from the radiation outside. It's as though the black hole and its emitted light remain in a long-distance relationship, not in terms of message passing, but in the structure of reality itself. This idea has found mathematical support in certain toy models, especially ones inspired by quantum computers and simplified gravitational systems. Researchers have even shown that quantum teleportation, a process where information is transferred using entanglement, can be understood as sending data through a wormhole in some setups. In other words, the act of entangling 2 systems and sending information between them may, in the right context, be indistinguishable from forming a tunnel through space and passing something through it. Now, does this mean we could one day throw a book into a black hole and retrieve it by catching a photon on the other side of a wormhole? Not exactly. The geometry involved is subtle, fragile, and only well understood in simplified models of the universe. But what the EPR idea suggests is that information doesn't need to cross the event horizon in the traditional sense. It may already be connected. It may always have been. And those connections may follow rules so different from our daily intuition that what seems like loss is really just translation. From one kind of order to another. It also hints at a larger truth, that space itself may be constructed from entanglement, that the fabric of reality isn't built from atoms or energy, but from the relationships between them. If you untangle the universe too much, it doesn't just lose structure, it loses shape. And once again, black holes are the stage where these ideas play out most vividly. They force us to consider realities where geometry is not fixed, where information is a thread that stitches space together, and where even the most extreme object in the universe might just be a mirror reflecting a deeper truth about how everything is connected. EPR is not a final answer. It's a doorway, one that doesn't swing open easily, but one that may, in time, offer a route through the paradox, not by denying the weirdness, but by embracing it, by letting the strange connections remain strange, and by trusting that underneath the complexity the universe still keeps its promises, even when it builds a tunnel through its own reflection. And now, as we near the end of this long and winding path through the cosmos, perhaps we can begin to let go, not of the questions, but of the pressure to answer them. Because some stories are not meant to close with certainty. Some are meant to leave you wondering softly in the quiet space between thoughts. Black holes are no longer what they seemed when we first imagined them. They are not simply monsters that devour or voids that erase. They are not blank, bald, or mute. Instead, they whisper through paradox and symmetry, through curvature and entropy, through radiation and information. They are places where physics becomes poetry, where silence is filled with memory, where simplicity wears a mask and secrets are kept in plain sight. What have we learned, really? That black holes are described by only 3 numbers, and yet hide within them more possibilities than we can count. That their surfaces hold more information than their volumes could explain. That they radiate without glowing, evaporate without touching, encode without showing. That they are in essence shadows, but not empty ones. We've walked alongside Hawking, who found that black holes are not entirely black. We've listened to Bekenstein, who taught us that entropy can live on a surface. We've seen string theory try to count the microstates hidden beneath simplicity. We've traced entanglement across horizons and imagined wormholes opening between distant particles, and still the centre remains quiet. Not because there is no answer, but because the question itself stretches, longer, deeper, more beautifully confusing, each time we ask it. What is a black hole? A collapsed star? A curved space? A hologram? A mirage? A vault of secrets? A mirror for the universe itself? Maybe it is all of these, or maybe it is something else entirely, something we have yet to name, and yet it holds a lesson even now, even here at the end of the path. It tells us that the world is not always what it appears to be, that boundaries may hold more than depths, that what is lost might not be gone, only translated, that simplicity can be deceptive, and complexity need not be chaos. It tells us, too, that we ourselves are not separate from this story. You, who are made of particles born in stars, of atoms forged in furnaces older than Earth. You, who hold in your thoughts the same paradoxes that haunt the horizon. You, who ask and listen and try to understand. You are part of this mystery. You are part of this question, and that is not a small thing. Because when you wonder about black holes, you are also wondering about yourself, about the nature of information, about what it means to remember, about what it means to be known, or forgotten, or folded into something larger than you can see. You are not outside the universe looking in. You are woven into it. Your thoughts are curves in space. Your memories are ripples in entropy. Your questions are echoes of the same question the universe keeps asking itself again and again in stars and equations and shadows. Can something be both simple and infinite? Can it vanish and still remain? Perhaps. Or perhaps it doesn't matter. Because even if we never solve the paradox, even if firewalls remain mysterious and wormholes never form, even if the hologram flickers and the microstates blur, we're still left with something precious. We are left with the wonder, and that, in the end, may be the best kind of answer. Not one that closes the book, but one that lets it rest, half open, half remembered, still breathing. So now, feel free to close your eyes. Let the weight of the day slide away. Let the stars outside your window fade into soft blur. The black holes are still out there, quiet and unhurried, not watching but waiting, not waiting to be solved, just to be noticed, to be imagined, to be dreamed of. Sleep well, little shadow of infinity. Sleep well.